Hi, yes, I'm Julien Brenneck. I'll be talking about some recent work I've been doing on iterative methods for contour-based nonlinear eigensolvers. Um, and I guess the goal of most of this work and the work in nonlinear eigenvalue problems in general is sort of a black box solver where you don't need any particular, you can just run it on any problem and it generally would work. And a quick review of the nonlinear eigenproblem. We have some holomorphic or meromorphic matrix valued function on some region of the complex plane. And the eigenvalue problem is just asking for what vectors and eigenvalues do we have zeros for this eigenvalue equation. And if we just take the regular matrix pencil, then we recover again the standard linear eigenvalue problem is one way to view this. And there's a good review paper by Goodall that covers all of the different techniques in the nonlinear eigenvalue problem. That's very good. So the main previous techniques are roughly categorized into three types. The one I'm talking about mainly is the contour-based methods. Specifically, this is building on the work by Bine and NL Feast, which is done by some of my collaborators. And I won't talk so much about the Sakurai methods, but they are conceptually very similar. And the other types of methods are Newton and approximation methods. And approximation here means doing an approximation of the operator T, either a polynomial or a rational approximation. The only Newton method I'm going to mention is the residual inverse iteration, which is used by NL Feast to iterate in a particular way. And most of these methods, like NL-eigs and Quark, that are relatively good methods to use. These are sort of like the main ones people are working on right now, I think. There's a combination of both the Newton and approximation type methods. As with NL Feast, there's a combination of both the contour and the Newton type methods. So just a picture of what we're sort of thinking about in terms of these contour solvers is that there's some region of the complex plane with the spectrum that we want, and we enclose the region of the spectrum that we're trying to solve for within some complex contour, and then we numerically approximate the contour with these quadrature nodes. And a lot of the numerical details come through what happens at these quadrature nodes where we solve some linear system. So an overview of Bine's method. So there's a Keldysh theorem that we use to essentially decompose the operator or the resolvent of the operator locally. And this is sort of, I mean, this is a lot of equations for this, but we have some contour that we localize the spectrum within, and then we apply some function, and then that function is applied locally to the spectrum. And here this is the Jordan decomposition of the operator in the contour. And then we for this function, we use monomials as sort of a monomial basis, and we end up with these moment matrices. And if we look at the 0th and the first moments are the ones we particularly care about, there's sort of a simple way of interpreting it. There's different powers of the spectrum. And from now I'm going to assume that it's locally diagonalizable, so it's not really a Jordan block, but a diagonal block of eigenvalues. And then Bine's method in particular, you take a decomposition of this A0 matrix, and then through some similarity transform, we can compute the eigenstructure, the right eigenvalues V and the eigenvectors lambda. And this is a very good method in particular because we can use any type of nonlinearity. We don't have to use, like, for example, an approximation of it. It just directly works on any type. So we can do, of course, polynomial and rational, but fully nonlinear ones as well. And it's highly parallel. We can parallelize across each of the contour nodes. At each one, we solve a linear system, but they're each independent. And we can do spectral slicing, which just means we can choose any region of the complex plane to include within our contour and only solve there. And this generalizes to higher moments, which is in general necessary for the nonlinear problems because you have issues with deficient eigenvectors. And there's a proof of convergence in Bine's paper, and there's a nice convergence in the number of quadrature nodes. The main drawbacks are that it can be very expensive. You have to solve maybe a few hundred of these linear systems of the size of the operator, and they need to be solved relatively accurately to the accuracy of the solution that you want. And there's no way to necessarily iterate this method other than maybe an adaptive quadrature. But in general, you need to know how many nodes to start with. It's kind of, there's no way to know. You have to run it, and then you might not have an accurate enough result and have to rerun it with more contour nodes. In addition, it can be very difficult to position the contour nodes far away from the eigenvalues, which for iterative linear solves makes the linear systems very ill-conditioned. And here's a picture, for example. You can see this eigenvalue becomes very near the contour node. And when there are many contour nodes, that's very difficult to avoid in general. And so next, NL feast. So the main idea is to use this residual inverse iteration, which was initially proposed with a single sort of fixed shift or moving shift, but this uses the contour points themselves as fixed shifts each iteration. And we end up with this Newton-type iteration on the eigenvector subspace. Here, this is just essentially applying t to x at each lambda and taking the residual in a block form. And this forms this projection matrix, which is very similar to, of course, linear feast, hence the name. But at each iteration, we form this reduced projected problem, and we solve this. So it's much smaller, but it's still just a new nonlinear eigenvalue problem that we have to solve. And this, there's no proof of convergence yet. It seems difficult to do, and there's not really a clear way to do it. But it has the same convergence properties of linear feast, experimentally at least, which is very good. And again, like Bind's method, it's highly parallel because we can parallelize across the contour nodes. And additionally, we can solve linear systems to relatively low accuracy, and we do this in the current implementation, which is right now for polynomial only, but will be for fully nonlinear in the future. So one of the main cons is that this is really only a projection method, and for polynomial, we can use the companion problem at the level of the reduced system and essentially just solve it directly. But for non-polynomial, you have to use an internal method to solve the reduced system itself. One sort of natural choice that we found was to use Bind as the internal solver, but it's still not so clear-cut, even though there's a contour within the contour. It's not always necessarily clear that you want to use the exact same contour. For example, the feast convergence depends on having some of the spectrum outside of the contour for convergence, whereas Bind really only captures within. And additionally, Bind's method, we might need many more contour points because we want the solution to the reduced system to be relatively accurate, whereas we don't need so many contour points for feast convergence. So I guess the main like practical difficulty is just then you have a second method you have to configure within the first method, and it's not really clear how to do that. So when working on these, I sort of, the question that led to this work was how do we share the contour nodes between NL feast and then the internal Bind solve, and that would also solve the linear systems simultaneously for both. And then another perspective is how can we sort of iterate Bind's method, because that would sort of address drawbacks of having to use many quadrature points for that. And I guess motivated by those, I sort of tried to combine them and found a sort of hybrid algorithm that we can use to iterate these contour methods. So generalizing the residual inverse iteration moments of NL feast, we just add this monomial term as in the moments of Bind's method. And then again, we use the residual inverse iteration. And then the similarity transform and all of that to find the spectral information is the same as Bind's method. One thing to note, though, is that these moments are distinct for nonlinear problems from the actual moments of Bind's method. And I guess it's not clear how we should interpret the difference, but we are solving a different problem. Here's just an overview of the algorithm quickly. So we solve for these moments by solving linear systems, and then we compute a decomposition. and solve for the eigenstructure. And then in this block right here in blue, there's one way to view this, is that this first step is literally just Bind's algorithm, and then we start converging through the NL feast type iteration. And that's how we can view this as a hybrid algorithm. So while these two sections are sort of the same, the only really distinction is that here we're using the residual inverse iteration, whereas here we don't necessarily have to in the first iteration. So from one perspective, this is NL feast using Bind's decomposition directly with no reduced system, which removes all of the difficulties of having to solve an internal method. And then from the other perspective, we can view it as Bind's method being iterated in the NL feast approach using the fixed contour shifts of residual inverse iteration. And one of the main theoretical benefits of this is that it reduces directly to standard feast for linear problems, which might lead to being able to use the convergence proofs of linear feast in a way to extend it here. And it also just clarifies some ways of how we can view feast in a nonlinear context. And some numerical results. So again, like I said, the first iteration is literally just Bind's method in a way. So we can compare it directly to the first iteration to compare to Bind's method. And we see nice convergence, relatively similar to feast convergence. The main thing to look at then is the linear system solves, the number of linear system solves needed for convergence, because that's the main computational cost. Here, there's a few less for these hybrid method solves. There's Bind uses around 256, and these are a little bit under that. But the main savings is that we can factorize once, store the factorization at each of the contour points, and then reuse them, which is very quick. So the successive iterations are very fast. So the main computational cost becomes just these 16 or 32, for example, factorizations, versus Bind where we need 256. And this is the Heddler problem is a fully nonlinear problem, which is more the type of problem we would expect this to be useful for. And it's similar results where roughly the same number of total linear system solves as Bind, but many fewer factorizations. And we also, of course, don't need as many contour points. And in this case where all the spectrum is real, we can then distance the contours nodes from the real axis and ensure that we have relatively stable linear systems if we were solving iteratively as well. In general, we have to use these higher moments. I'm not really going to talk about them, but we just essentially form these block moment matrices and then solve as we did before. And the SS Hankel method here would be very good. It would make these much smaller in memory, but have not figured out how that would work yet. And there's also some problems about we have to deflate the subspace iteration. So most of the future work then that's left is to figure out some of the details of the higher moments. There's also no proof of convergence. There's no analysis of this contour shifted residual inverse iteration either for this method or for NL feast. And there's also this opens up more questions and answers some about how we can view the theoretical relation of this algorithm to the other algorithms and understanding NL feast and linear feast. And this exists right now in the feast solver Julia package that I've written. There's also the feast Fortran library, the reference library that currently has a polynomial solver and will have a fully nonlinear solver. The Julia one is much less optimized than the Fortran code, but it's much more extensible, and it will hopefully be compatible with any PPAC. If you need that, let me know. Also, there will eventually be feast bindings in Julia if I can figure out some compiler bugs. Thank you. That's the whole talk.
Right. So thank you very much for the nice talk. Are there any questions or remarks? So here is a question, two questions. What is the greatest barrier in establishing convergence results for NL feast and the combination with Bind?
I guess, so we can have some kind of idea of convergence in terms of the quadratures as Bind did, but I don't think there's any clear way of understanding the convergence of the residual inverse iterations themselves. And I haven't really worked on that. Some of my collaborators have worked on that, and it doesn't seem like there's a clear way to approach it.
All right. And then there's a second question. How does your method compare with NLEIGS in terms of linear system solvers?
I have not compared it with NLEIGS in terms of linear system solves. That would be a good comparison to make, I guess, but they are sort of distinct in a way that this solves any general problem versus, I think NLEIGS does too, but no, I haven't compared them.